Okay. Last class, last week we talked about the first notation to implement integer called SS notation. And this week we will wait. 等一下啊。Okay, and this week today we'll talk about another implementation of integer notation in computer system. We call it two's complement notation. Two's complement notation. Okay, two's complement notation. It is the most popular system for representing integer in today's computer. Okay, so you have to know it. In your PDF handout on page 39, you can see a figure 1-16, which is also shown on the screen. This is a typical and a small-scale representation of integer by two's complement notation system. Okay. Supposedly, if we use only 3-bit, this is the 3-bit using two's complement notation to represent integer. I have to emphasize, it is represent integer. It is represent a character or a floating point number or other type of it in data type. It will represent different information. But in here, it represents integer. Okay. And we know that if we have a 3-bit, okay, we have 3 bits. So how many kind of bit value can be represented by 3-bit? Okay. The first bit we have 2 choices, 0 or 1. The second bit we have 2 choices. The third bit we have 2 choices. So is 2 to the power 3 is equal to 8. So using 3-bit, you can have a value to be represented. Okay, you have a kind of value can be represented using 3-bit. And what are these a value is here. Okay, this a value is here, and the value is between positive 3 and -4, including 0. So you count how many number here is 8. We have a value can be represent the content of 3-bit. Okay, and by observing this bit pattern, we can find out that so-called most significant bit or leading bit or leftmost bit, okay, which is this color, this part. Now, if we take a look at this part, we can find out in the first bit, the leftmost bit is 0. It represents positive number or 0. If the first bit is 1, it represents the number is a negative number. Okay? Now, For positive number, positive integer, or zero integer is easier to identify because you can simply convert this binary system, the bit pattern, just interpret as a binary system. It's a base 2 system. Then you can get the positive number it represents. So 1, 1 is what? Is 2 plus 1. So it's 3. 1, 0 is 2 plus 0 is 2. Okay? 0, 1 is 0 plus 1 is 1. Okay? And 0, 0 is 0 plus 0 is what? Is 0. Okay? Now, the difficult part is the negative size of the representation. 1, 1, 1 represents minus 1. 1, 1, 0 represents minus 2. 1, 0, 1 represents minus 3. Why and how to interpret this bit pattern into a negative number? Okay, let's go back this later. Now let's take a look at a 4-bit system of two's complement notation, which is shown here. Okay, now again, the first digit, the most significant digit, okay, the leftmost digit is 0, represent a positive value or 0. And the leftmost bit is 1, represent is a negative number. Now, for positive and 0, it's easier to interpret. How to interpret is using base 2 system. So 1, 1, 1, 3, 1 means 4 plus 2 plus 1, which is equal to 7. Okay? 1, 1, 0 is 4 plus 2 plus 0 is equal to 6. 1, 0, 1 is 4 plus 0 plus 1 is equal to 1. Okay? And 0, 0, 1 is 0 plus 0 plus 1 is equal to 1. Blah, 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 blah. Okay? And the 0, 0, 0, of course, is 0 plus 0 plus 0 is equal to 0. Again, the difficult part is this part. How you tell the negative value by look at this bit pattern. 1, 1, 1, 1. 4 consecutive 1 represent minus 1. How you do that? Okay? Now, before we go on, I have to repeat it again. If you want to interpret positive number, it is easy. It's starting with the first bit as 0. And using a base 2 system to convert to to convert to decimal system, base 10 system, which I think everybody can do that. This positive side is easy, but the negative side, how you do it. Okay, so this is why I just say that size bit is the most significant bit, the leftmost bit. 0 represents positive or 0 value. 1 represents a negative value. To interpret positive value is easy. Okay, it's just simply convert a base 2 system into base 10 system. Okay? Or reversely, you can do is convert base 10 system into base 2 system. Okay? So let's go back here. In decimal system or base 10 system, you have a 4. Okay? A value of 4. Not 4, that is 3. Okay? If you have a base 10 system, you have value, okay, of 3. Now, 3 is equal to what? 2 plus 1. Okay? So, convert to binary system is 0, 1, 1. Okay? So, in 2's complement notation, okay? 2's complement notation. In 2's complement notation, okay? You want to represent a decimal value of 3. In 2's complement notation, you should use 0, 1, 1 as the last 3 digits. And the first digit is 0. So overall you get 0, 0, 1, 1. Okay, let's see. 0, 0, 0, 0, 1, 1 is a 2's complement notation for positive 3. Okay, so positive value or positive pattern in 2's complement notation is easy. The difficult part is the negative value. Okay, so how to do negative value in 2's complement notation? There are 3 methods discussed in this handout. Okay, the first method is you using the positive representation and subtract from 1, 0, 0, 0, 0, 0, depending on how many bits you are using. If you using 4-bit 2's complement notation, there will be 4 0 here. This one is kind of an extra bit. Okay? Now, take an example. How you represent -3 in 4-bit pattern? Now we know 3, positive 3. Okay, positive 3 is stupid. Positive 3 is 0, 0, 1, 1. This is bit 2's complement notation. Bit pattern for 2's complement notation of 3. Okay? Positive 3 is 0, 0, 1, 1. And how you get negative 3? The 2's complement notation. How you get 2's complement notation for negative 3? Method number 1 tell you that you write down 1, 0, 0, 0, 0. How many 0? 4. Because you're using 4-bit pattern. Okay? So you're using 4 0. And in this one, the leading one is kind of extra one. Okay? Then this base 2 number subtract by 0, 0, 1, 1, which is the bit pattern for positive 3. So 0, 0, 1, 1, and you subtract. Okay? Now, 0 minus 1. 0 cannot minus 1. So you had a dollar 1 from previous position. Okay? So you get 1. And in order to borrow one from previous position, you have to borrow one from previous position. You have to borrow one from previous position. Now, since it already been borrowed one from this log, the rightmost digit, okay, it will remaining one, and 1 minus 1 becomes 0. And since it already been borrowed by 1, okay, the remaining is 1. So 1 minus 0 is 1. Okay? It already been borrowed 1. So it got 1 left. 1 minus 0. 1 minus 0 is 1. Okay? So this is our answer for two's complement notation for minus 3. Did we do it right? Let's check. Check the table. Okay? Minus 3 is using 1101 to represent. Minus 1 we use to calculate is 1101. So we got the right answer by using the minus 1. Okay? Take another example. Minus 5 in 4-bit notation. How you going to get it? Now, positive 5. Positive 5 is what? Is 4 plus 0 plus 1. This is 1 is 2 to the power 0. This 0 is 2 power 1. This 4 is 2 power 2. Okay? So 5 can be break down into 4 plus 0 plus 1. Now, so its base 2 representation is 101. Okay? Base 2. Now, how we get minus 5? Same thing, same method. Okay? Using minus 1 is 1 0 0 0 0 because we are using 4-bit, so we have 4 0 here. 5 two's complement notation is 1 0 1 minus by 101. So 0 minus 1, we have to borrow 1. It is 0, so borrow 1 again. It's 0, so borrow 1 again. Okay? Now, once we borrow 1, and which in English, in pronunciation, is 2, okay? But in binary system, we don't have 2. Okay? But in English, it's 2, okay? 2 minus 1 is 1, okay? And since we here been borrow 1, so we got 1 left. So 1 minus 0 is 1. It been borrowed by 1 from previous digit is 1. 1 minus 1 is 0. And it's been borrowed by 1. And 1 minus 0 for 4 digit, we have to add leading 0 in front to get 4 bit. Okay, so it's 1 minus 0 is 1. So minus 5 is bit pattern is represented by 1011. Let's take a peek. See if we get the right answer. Minus 5 in two's complement notation is represented by 1011. Yes. Yeah. We do it right. 1011. Okay? So we just using a very small scale of tooth complement notation to demonstrate how to represent negative number in tooth complement notation. Okay? There's another method. Method number 2 is kind of easier without doing any mess, just doing the so-called complement. Okay? Complement is easy. If you have a 0 now, you change to 1. If you have a 1 now, you change to 0. Okay? So 1 change to 0, 0 change to 1. Okay? So 1, 0, 1, 1. You just do the complement. Okay? Just complement this bit pattern. It will become 0, 1, 0, 0. Because this 1 become 0. This 0 become 1 here. This 1 become 0 here. This 1 become 0 here. And 1, 0, 0, 0 will become 0, 1, 1, 1. Because you do it big Y complementation. 1 will become 0. 0 will become 1. 0 will become 1. 0 will become 1. Okay? This is so-called complement operation. Now, to convert a positive tooth complement notation into negative tooth complement notation, you can use this complement operation. And how you do it is, you're starting from rightmost bit and going to left side of the bit pattern until you find the first one. Okay? Until you find the first one. Then starting from the left of the first one, you do all the complementation until all the bit pattern is finished. Okay? So let's take an example. 2 in 4-bit tooth complement notation is 0, 0, 1, 0. Okay? And minus 2, how you get minus 2 tooth complement notation is you're starting from the right of the bit pattern and then go left until what? Until you got the first one. So this is the first one you encountered here. This is the first one. You from the rightmost bit and going left. Once you got the first one, okay, this is a 0, so we cannot count. But when you got the first one, you do the complement for the rest of the binary digit. So you copy your 0, you copy 0. You got 1, you copy 1. But since you got the first one, from here to the leftmost bit, you do complementation. So 0 have a complement of 1. 0 have a complement of 1. And this bit pattern, okay? This bit pattern is minus 2 representation. Let's take a look at minus 2. The bit pattern is 3, 1 and following by a 0. Okay? So now 5. Tooth complement notation leading by 0 is positive. Okay? Then 5 can break into 4 plus 0 plus 1. So it's 1, 0, 1. And how you get minus 5 is starting from the rightmost bit. Starting from rightmost bit when you encounter the first one, so this is the first one you encounter, and you just copy, and the rest of the bit you do complement. So 0 become 1, 1 become 0, 0 become 1. So 1 0 1 1 is the bit pattern for -5. Okay, so let's take a look at -5. The bit pattern, the corresponding bit pattern is 1 0 1 1. Okay, -5. Bit pattern is 1 0 1 1. Okay, so this is method 2, and then there's a method 3. Okay, this figure 1-17 is just the method 2. I just tell you. Okay, now method 3. Method 3 is slightly complicated, okay, but it is still easy. It's complement the entire pattern and +1. So 5. Now we're using 8-bit, okay? Using 8-bit. So 5 in 8-bit post complement notation is 0 0 0 0 0 1 0 1. Okay? Because we are using 8-bit, so we require a binary value here. Okay? Now, how we get the representation of -5? Because right now we know +5 is this guy. Now, -5 is what? Method 3 tells you that first you complement the whole pattern. So 1 becomes 0, 0 becomes 1, 1 becomes 0, and then over this 5 0 becomes 5 1 here. And then you +1, just +1. Okay, you will get this one. You will get this final result. Okay, because 0 + 1 become 1 here, and the rest of the binary value is the same. And this guy is -5. Okay. It consists with what we just say that the first bit is what? Is 1 represent is a negative value. Okay, so in 8-bit 2's complement notation, to represent -5, you need to use this one. Okay, this is the answer. Okay, so the above 3 methods work in reverse. What does it mean? What does it mean? You can convert +5 to -5. All these 3 methods. Or you can convert -5 into +5. So when I give you a bit pattern like this one, 1 1 0 0, and in decimal system, in base 10 system, what's the value it represent? I don't know. Okay? I have to do some math to determine what's the value, because it's starting with 1, which means this value is a negative value. It's negative. So in negative, we cannot determine right away. So in order to determine its value, how we going to do? We use all three methods can be used, but the method 2 is most easy one. How to do it? We're starting from the right, okay, of the bit pattern, and find the first one. So we get 0, 0, 1. And then the rest of the bit pattern, we do complementation. So become 0, 1, 0, 0. So we do not know what this value represents, but we know what the value it represents. We're using method 2, okay? 0, 1, 0, 0 is equal to what? 4, 2, 1 is their corresponding weight, and we have only 1 here. So this number, this bit pattern represents positive 4. So this guy represents what? Negative 4. So 1, 1, 0, 0. Let's check the table. 1, 1, 0, 0. Okay, 1, 1, 0, 0. Actually, it is -4. So, okay, so all three methods are work in reverse. It can change from a positive value to a negative value. Similarly, we can change a negative value into positive value. Okay, we are talking about the tooth complement notation here. So it is easy to convert in back and forth. Okay, back and forth. Okay, positive to negative, negative to positive is very easy. Okay, the most easy one is method 2. So if you want to pass the exam easier, you have to at least remember one method, and I would suggest you remember method 2, which is easy. You don't need to do any mathematics in base 2 system. Okay. And the popularity of tooth complement notation has a reason. The reason is following. Okay, in the science bit, the demo speed is 0, so we can decode through normal binary representation. Okay, normal base system. Okay, to change into base 10. Or decimal system. If the size bit is 1, it's difficult to tell, okay? But it's easy to use the above 3 methods to change into corresponding positive value. Then you can decode it as the case of 0 sign bit, okay? So how to decode 1010? You find sign bit is 1, so it's a negative value, and negative value is difficult to tell. So how you decode this 1010? You use method 2, okay? Starting from right, and find the first one, which is here. So 0, 1, and the next 2 binary value you do complementation, which is 1, 0. Okay. Now 0, 1, 1, 0. Sign bit is 0, so it's a positive value, and this bit is 4. This bit is 2. This bit is 1. Okay. So this guy 0, 1, 1, 0 represents positive 6. So this guy represents what? Represents negative 6. Okay? Now, another reason for the popularity of the two's complement notation is the simplicity in addition process. To do addition in two's complement notation is very easy. To do addition in two's complement notation is very easy. How easy is that? You just doing like you are doing in base 2 system. You just can ignore whether it's a positive value or negative value. You just using the two's complement notation to do the binary addition. What's the binary addition? 0 plus 0 is 0. 0 plus 1 is 1. Okay, 1 plus 0 is 1. 1 plus 1 is 1, 0. Okay? Now, let's go back here. We know 1, 0, 1, 0 is represent minus 6. 0, 1, 0, 0, 1, 1, 0 is positive 6. So, we can forget about what's the actual decimal value for this for this 0, 1, 1, 0. You can forget about it. Okay, you don't need to do the interpretation. What 0, 1, 1 representing, it doesn't matter. Okay. So we put it down 1, 0, 1, 1, 0. Now, this pattern is actually represent minus 6. Now you can 1, 0, 1, 0. You can forget about it. Forget about it is actually represent negative 6. So you just take these two binary value 0, 1, 0, 1, 0, and then you add together. So what you will get is 0 plus 0 is 0. 1 plus 1 is 1, 0. Okay? 0 here. And then you carry over 1 here. 1 plus 1 is 1, 0. Okay? And then you carry 1 over here. So 1 here. 1, 1 is 0. And then you have 1. And this 1 is extra 1. In two's complement notation, when you do a computation, originally you have 4 bits. You got the extra 5th bit. You just get rid of it. You just throw it away. Okay? This 1 you can just forget about it and just take it off. So what you get is 0, 0, 0, 0, 0. So when you take a bit binary notation of the bit pattern 0, 1, 1, 0, you want to add another bit pattern 1, 0, 1, 0, and then you forget about minus 6, and you forget about positive 6. You just add this two's complement notation, and you get the answer. And the answer is, in fact, is what? 0. In base 10 system. Because the first bit is 0, and the other 3 bit is also 0. Okay? So when we do the validation, positive 6 plus minus 6, positive 6 minus negative 6 is equal to 0. So we got consistent result here. Okay, so the reason we're using two's complement notation is the easier, it is easy to do two's complement notation addition. Okay? Okay, simplicity of addition. Now, here is another example of adding two values, and both of them are in two's complement notation. 0, 1, 1, 1. What does it represent? You don't mind when the computer do the addition. Computer doesn't take time to interpret what is the decimal value, what's the base 10 value. 1011, the same. We have two integer value represented by two's complement notation, and then we do addition. So this is what we got. When we have a two 4-bit two's complement notation. When we do addition, we got the extra one, the fifth bit, the fifth binary value. We just truncate, okay? We just delete or remove it. We just forget about it. So when we do this two values addition, we got 0, 0, 1, 0. Okay? And then you can do an interpretation. Now, let's do a final check. Okay? 0, 1, 1, 1. What's the value it represents? 1, 0 is 7, right? This is the two's complement notation for 7. Okay? And 1011, which is a negative value because side bit is 1. 1011, let's find out 1011. What's the actual value? 1011 is here, minus 5. So this guy is minus 5. Stupid. Minus 5. So positive 7 and a minus 5. And we just say we discard the extra bit. So we have a 0, 0, 1, 0. Let's find out. Let's check the table. 0, 0, 1, 0. 0, 0, 1, 0. Here is positive 2. Okay? Let's go back. This is positive 2. Okay? So 7 plus minus 5 is equal to 2. Okay? When you do the binary addition in two's complement notation, you get a correct, okay? Correct answer of decimal system. Okay? Let's take a 10-minute break now.